was created with one purpose and one purpose only, which is to facilitate the quantum leap to renewable energy. That's why many of us have joined York University to make that happen. And of course, we have 3 tracks, pedagogy, research, and knowledge mobilization, which is what today is all about. This is part of a seminar series where we're bringing cutting-edge people to Toronto to provide their insights on how we can do this quantum leap to a sustainable energy society. And the point of the story is to gather that knowledge to be able to provide a roadmap of renewable energy. So the decision makers, the policy makers that create the frameworks that make possible to either remain stuck on the 19th and 20th century can see that it is possible to move into the 21st, 22nd century with new ways of doing things. The next thing I want to say to you is that this production of roadmaps requires people of ingenuity, creativity, and most important, valor. We have to be brave because most of the time we're told by the status quo that things cannot be different. And our next speaker is somebody that has all those characteristics. He believes in ingenuity, he practices what he preaches, and he's also a very brave person. And when I was introducing him to some of the guests that we have from Europe right now, I say that he basically is a scholar among scholars. And he said, Jose, I'm really simply a venture capitalist that understands climate change. So that's what he told me he is. But I actually would like to put one last thing about that. He's actually an angel venture capitalist. And I like that part, the angel part. When people talk about angel capitalists, there is such thing. There is people that actually are willing to put their energy and their resources to ensure that good things happen. And my friend Tom Rand is one of those people. So without any further ado, why don't we give him a round of applause if he feels comfortable. So,
I don't know if it's applause that makes me feel comfortable or just being amongst friends. So I'm going to keep my remarks fairly brief. I know you have a busy day. I'm going to talk in particular about a project that I'm involved with here in downtown Toronto with the building. It's a very practical example of the kinds of things we can do in the short term. But I want to put things in a slightly larger context just to sort of set the stage. And I mean, it's a great photograph, the kind of context in which I think we need to think as we get bogged down in details of grid balancing and frequency regulation and all that kind of stuff. And I'm a country boy, so I like to think of trees as a good analogy. I'm from Niagara-on-the-Lake. And if you think about a tree, the tree, there's fruit at the top, the middle, the bottom, and the fruit is carbon, right? Our carbon emissions. And we need to pick every piece of fruit from this tree, right? And we have to do it quickly. It's not optional that we pick all this fruit. And I think I'm probably preaching to the choir when I say this. I mean, the urgency of this problem. The International Energy Agency came out, very conservative organization. I mean, these guys are set up to counterbalance OPEC, to talk about energy security for the Western world. This is as sort of blue blazer, gray pant a group as you can possibly get, right? Very conservative group. They've always put climate change as a footnote in their reports to Western governments about energy around the world. They finally sort of came out of the closet on climate change and sort of acknowledged the scope of this problem. So when the International Energy Agency, as conservative a group as they, say that we're on track right now for a 6-degree temperature rise this century. 6-degree temperature rise. I mean, this is all a dream. It's a bubble we'll look back at with great fondness if that kind of stuff hits. So the severity of what's coming cannot be underestimated. And it's not optional that we pick every piece of fruit on this tree, to sort of switch metaphors very quickly. The problem, of course, we have is we think about clean energy and smart grids and solving this problem. We think about the fruit at the very top, right? Giant solar plants in the American Southwest, wind plants covering the continent, and a continent-wide energy internet backed up by storage. This is entirely possible. I've written about it in my book, but it's very, very difficult to do. It requires political cooperation. It requires trillions of dollars of capital. You need to build a whole lot of scaffolding up that tree to pick that top fruit, right? And that includes political will, that includes consciousness amongst the public as to how urgent this problem is, yada, 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 yada. That's really difficult fruit to pick, but that's the fruit we see when we look at this tree. And so we get daunted by that task of climbing to the top of this tree and picking that fruit. And there's, in the middle, there's some fruit that's a little harder to get. The Green Energy Act would represent that middle ground, the first steps we might take. But sitting right in front of us at eye level and sitting on the ground, ready to be picked up, is some really low-hanging fruit. So this building that I built, or I'm the co-developer of on College Street, is what I claim is North America's greenest hotel. And obviously by green, I'm not talking about, organic granola and recycled toilet paper. I'm talking about carbon. Right? When we speak about green buildings, if we're not talking about carbon, we're not playing in the big leagues. And what I've proven with this building, it's very simple. I've reduced our carbon footprint by 75% from business as usual, and I did it at a profit. So there's 2 points, and the technology's bog standard. I mean, geothermal heating and cooling, solar thermal on the rooftop, some solar PV under the Green Energy Act, a very small piece of it, drain water heat recapture, LED lighting, smart thermostats, good insulation. It's not rocket science. I mean, I knew nothing about the built environment when I got into this project. I really used it as kind of a laboratory, a living laboratory for my own investment fund to find out what technologies perform in today's marketplace without a subsidy, and that's the kind of company I need to invest in. So geothermal company came out of that process. But what I found out was, I was like, well, how do I do this? 75%, is it possible? I had absolutely no idea. It turns out it's so easy, it's disturbing. None of this technology has technology risk, right? It's been around for a long. LED lighting maybe is the newest stuff, but it's not a big risk to put in some LED lighting. We light up the whole building inside and out for less energy than a hairdryer, right? So this, it's actually really easy to do. And that's the part that was so disturbing. So I look at things, I have great respect for people that put their money where their mouth is and build LEED Platinum buildings and so on, but you can be LEED Platinum and reduce your carbon by maybe 25%, which is an absolutely insufficient response to climate change, right? We know with climate change we need to reduce our global emissions by 3/4. That's why I set that target. It wasn't arbitrary. But the disturbing part is how easy it is to do. So disturbing in the sense that I don't see a lot of other building owners hitting that target, right? This building stands out. I mean, we get more press coverage on this building than I ever imagined, and that's great in a way, but in another way, it's kind of depressing, because why is my building so unusual? The point I'm making is that, the retrofits for my energy stuff, the loan payments on that retrofit is less than my energy savings, so I'm cash flow positive from day one. I have a payback period of maybe 5 or 6 years. So all we have to do is have all these building owners take a 5 or 6 year view, and I argue my model, 5% of the building's capital is all you need to retrofit it and get a 3/4 cut reduction. It scales right up to the Empire State Building. Back of the envelope calculations will confirm that. 5% of the building's capital, you unlock that in a mortgage, you retrofit the building, you lower your carbon by 3/4, and you're cash flow positive from day one, and it'll work for any building you see here. And you can retrofit these giant towers with geothermal now, by the way. You can drive a truck into the basement, electrically powered, fully recursive robotic drilling systems operating in 7'2" headroom. You can retrofit the Scotia Tower now. So there's no excuse not to put geothermal everywhere. So the disturbing part is how easy it is and how few other people are picking up that gauntlet that I've thrown down. We've been told from Ottawa time and time and time again, and this is not a political statement, right? Look, climate science is not a political issue. It happens to be an empirical fact. We can disagree politically on the best solutions, how to use the market, et cetera, but the fact of climate change is not a political statement. What is political is the economics of it. And we've been told time and time again that Kyoto is not something we can possibly meet, right? It's this huge mountain we have to climb, and even if we manage to scramble our way over it, we're going to arrive on the other side poor, disheveled, with our pockets picked. Kyoto's friction in the economic system. If every building owner did what I did, every building owner would be wealthier. It's Canadian technology, it's Canadian solar, thermal, Canadian geothermal, Canadian trades, Canadian electricians, Canadian windows, Canadian insulation, Canadian power pipe, Canadian LED lighting. It's 90% Canadian technology. So the economic stimulus effect outside of the building owners getting wealthier is enormous. You can't outsource a building retrofit to China, with the exception of the PV panels, unfortunately. But other than that, it's all Canadian economic development. So every building owner would be wealthier. We would stimulate a massive surge of Canadian economic activity retrofitting those buildings. And we would blow past Kyoto. Kyoto's, I don't know, what we had to 19%, I think, 9%. 30% reductions we could have gotten in global emissions nationally if we were just retrofitting our buildings, right? This is fruit that's lying on the ground. We get paid to pick it up. I'm wealthier as a hotelier for having done this. I may have noble purpose in my heart, but this is a hardcore business decision. I'm wealthier. Every building owner would be wealthier doing this. So the notion that we couldn't meet Kyoto is nonsense. Absolute patent. Now, the higher fruit, building a continent-wide energy internet of solar farms and biomass, and that's tough. That's the political fight of our lives, right? That's this generation's time at bat, and it's very late, and I don't know if we're going to do it or not. That's tough, right? That's a political fight. But the fruit that's on the, we can't even pick that up. We can't even have a government that encourages us to pick up that fruit. It's absurd. So the point I'm making with this building and with this, by giving talks like this isn't what I'm happy to help my friend Jose and help encourage people to do the right thing, work on the side of the angels and stuff. But look, if you've got social capital to spend, if you're a captain of industry or a leader in your community, stand up and talk about this issue. The International Energy Agency has confirmed that we are on track for a 6-degree rise this century. If you have social capital to spend, this is the time to stand up and spend it. Stick your neck out. And if you think it's difficult, climate science is complicated, positive feedback loops, all kind of stuff. Look, all you need to know, who's more credible, NASA or Fox News? Any adult can make that decision, right? Almost. Yeah, well, this is the point. If you're a captain of industry, if you're a leader in our community, I bet you've got the intelligence to figure that one out, right? National Academy of Science or an Exxon-funded think tank. It's more credible. That's all you need to know. And if you've got social capital, now's the time to stand up and spend it, right? That's the reason I talk about this building, right? The building's full. I don't need more publicity. What I need are other people like Jose, like Peter, to stand up, be counted, and affect the public debate. Because the scaffolding we're building in buildings and building smart grid and enabling, buildings, lowering our energy use and making buildings smart, that's the foundation of the smart grid. Right? Unless you have demand response on all this electricity, and unless you lower the overall demand, you're not going to build this energy internet and smart grid. It's impossible. So the first domino to fall are these buildings and this urban energy use. Right? Low-hanging fruit, sitting on the ground, at a profit, can do it today. So it's the first step in a long journey to the top of that tree and picking the really, really hard fruit. And that's going to be the political fight of our lives. If we can't pick up the stuff that's lying on the ground, shame on us. Anyway, so I encourage you to have a great day. Do when you're lost in the weeds, and there are lots of weeds and details to learn, don't forget to pick your head up and look at that big picture, because this is why we do what we do. This is the most important work in the world. Thank you very much.
Tony, you around for the morning, or
I have to run.
You have to run.
Yeah.
We got time for points of clarification. You mind taking a question or two?
No, not at all.
Okay. Any questions from one of our more inspirational speakers in Ontario, as far as I'm concerned? So, Tom, great job. Thank you.
Yeah, I think in terms of new build, I really agree with you. The extra costs for high insulation and solar are so small that it pays back very fast. But in terms of rehabilitation, I mean, if you look at European projects for rehabilitation, all building measures normally have payback times maybe more around 15 to 20 years. And I think that's the problem. If it would be 5 years, it would be not such a big problem. But if you really look at real buildings and all the corners and insulation and bridges, so it's not so cheap. So the payback is long, and there are many people, homeowners who are old, they don't want to invest. We have investors who can't put the investment transfer to the renters. And so there are a lot of financial problems.
Yeah.
And I have the impression that it's very optimistic of you, but we have very slow rehabilitation rates as well for this financial problem. And so
Yeah. That's a good point. Yeah, so not every payback period is 5 years on that level of carbon reduction. I would disagree respectfully. The commercial buildings, the big stuff, the big game, I would argue does have a 5-year payback. I mean, the Empire State Building just got redone. Don't forget, North American buildings are different from European buildings, right? I'm assuming we're starting from a lousier baseline. The Empire State Building just got redone. They had a 38% reduction in carbon use, and it took 1.8% of the building's capital, and that payback is 2.2 years. That's the Empire State Building, and that's not using geothermal, not using cogen. So I would argue that the vast majority of our commercial buildings do face a payback of around 5 years. Now, I agree, it might not be the same in the American Southwest where they don't have heating issues, but you know, I'm in Toronto, I'm picking the fruit I can pick, and I'm really speaking to Canadians, and I think our buildings, our commercial buildings, do have that kind of payback. Houses are different, I agree. Housing stock of individual homes does not have the same kind of profile. I'm speaking sort of, 12,000 square feet and up. So yeah, and there's lots of caveats in my overarching broad attack, but there's enough low-hanging fruit that what I'm saying applies to the vast majority of what we see here. And there are other problems, as you point out, the economic disconnect between who pays the energy bills and who bills the building, huge problem. Ways to sort that out, there's now notions of a geo-utility model, so pension funds come in with the funding, building owner doesn't pay anything to have that building retrofitted, and the geo-utility says, I'm going to charge the tenants at natural gas minus 10%, so everybody wins. So there are people working very hard to get around those economic barriers, but you're absolutely right. Building codes, economic disconnect between tenant versus owner, these are problems to solve for sure. They're soft problems in the sense that it's a decision we need to make. It's not a technical problem, and I guess I'm pointing out the technical possibility of these reductions. But I take your point. There's lots of caveats in what I said, but so, fair enough.
Yeah.
Just a quick question. Can you tell us the address of your hotel?
Wow.
357 College. You can't miss it. You can see the solar panels on the roof.
Great. Okay.
Thank you.
Oh,
One last question, Tom. Thank you. Two of the sectors, building sectors that are most energy intensive are the hospital sector on one side, the hotel sector on the other side. One of them, the industry group, the Ontario Hospital Association, engineers in that sector, in fact the whole sector has adopted and is going aggressively forward in a green direction. Whereas in the industry group, now that you are a hotelier, the Hotel Association of Canada, the Toronto Association of Hotel Engineers has basically ignored the subject, and in fact their green program, the Green Key program that you're aware of, is focused on the equivalent of what you denigrated before. So they talk about the towels and things like that. Why do you think one has gone in that direction and the other has basically stayed static, and what can be done to bring them on board?
Yeah, well, I'm not going to pretend I know anything about people's intentions. But, a guess would be that hospitals have probably a fairly informed and complex set of engineering problems to deal with compared to a hotel, and so maybe the head engineer is a little more cognizant of technical possibilities and so on, is more open to engagement on different kinds of refurbishment. And they do have a semi-public mandate, so they probably have in their culture the notion they're going to get engaged in some of these debates. I don't know, that's just a guess, right? So I don't know, but hotels are really, really easy, right? It's actually not that difficult to do a hotel. Yeah, the Green Key program, I think, is absolute nonsense. It's a voluntary thing. You send in a questionnaire and they send you back a little ribbon. Come on.
tell us what you really think. Okay, great. Thank you.
Thanks, Peter.
Thanks very much, Tom. So we're going to move through. I didn't introduce myself. I think most of you know me. My name is Peter Love. It's sort of a great event for me because I have a foot in both camps. I'm very proud to be a visiting distinguished research fellow at the Center for Urban Energy here with Bala, who's one of the first of the research fellows appointed. And I'm also an adjunct professor at York University where I teach a fourth-year course on energy efficiency, and I see a few of my students here, so that's sort of fun. And I do some other things on the side, and was with a government agency many of you would remember called the Ontario Power Authority. But I just wanted to say it's really interesting, the event here today, and first of all, the diversity of people we have, and you're going to see a sense of them. We have, Tom, entrepreneur, venture capitalist, hotelier, and a real leader. We've got a building scientist we're going to hear from the technical building side. We've got a scientist specializing in nanotechnologies and photovoltaics, someone focused on climate change policy and energy policy and employment impacts. And a physicist that's doing work. So you can get a sense of how broad the topic is. And I just wanted, I was struck when I was thinking about today that, and I'm going to change a story that was given by a guy named Don Tapscott. Many of you probably heard of him, you've probably been around. And he tells a great story, which is really interesting about how we are in a whole new age. And he relates it back to the Gutenberg development of the printing press. And what he said then is that this guy developed a printing press, really sort of to, and his initial thought was, we got all these monks writing out the Bible, so I'm going to do this thing so that we can print more Bibles. And I don't know where this is going to go, I don't know when anyone's going to buy it, but that was the purpose of it, basically, was just to, take a bit of time off the monks. But what it led to was a complete change of governments. The feudal system didn't work anymore, and eventually the monarchy fell. Complete change in religion. People now could talk to God and could read God's word themselves, didn't have to depend on this guy speaking Latin in front of a church. Complete change in finance. The way that people could finance through stock exchanges and move money around. So it had a fundamental effect on life with that, and they had no idea what was going to happen. And Don says we're at the same thing with digital, and it's as if we've printed our first Bible. It's come off the machine, and this is the Bible, and we have no idea where it's going to go. And I would just say the smart grid is a sort of microcosm of that. We're starting to develop it. I think we have no idea what the potential is, and there's all sorts of pieces that are going to feed into it, and it is going to be really exciting to see where it all fits, because no one's got a clear straight line. We're here, we're going there, which I think is really exciting for people such as myself who've been in the industry for a while, and for young people who are going to be part of this, of how this evolves and what it becomes. So delighted to be here, and delighted to have people come in and share experiences. As I said, we've got a very diverse panel, so I'll bring them up one at a time, and we'll hopefully have time for a few questions and answers. And our first speaker is Professor Russel Richmond from Ryerson University, and a civil engineer who specializes in energy efficient design and in understanding building science, how buildings work, how energy and moisture works. He teaches in the architecture school here at Ryerson. And Russell, come on up. You have a presentation? Yeah, I'll get it. Okay.
Thank you, Peter. Well, good morning, everybody. Thank you very much for coming. Let's see if this can get going. All right, as Peter mentioned, my name is Russel Richmond. I'm a professor here in architectural science, and I am an engineer by training. I teach architecture. A wolf in sheep's clothing is what I usually refer to myself as. And I'm going to, great segue in Tom's presentation. I'm going to try to hammer down some of the nails he threw at the wall and show my idea of how building scientists or the built environment can actually help the grid. And I'm going to begin the talk really briefly about my motivation. Motivation's personal. I mean, you can get a sense of Tom's motivation, and you need to look inward on everybody, on your own motivation. To me, the environment and future generations. These happen to be my future generations, but still, this is what drives me. The driving factors, we're delivering incredibly large amounts of energy to both the suburban and the urban aspects. And this is my best representation of what me, the civil engineer, is looking at. And this is the grid to me. And perhaps someone who's really, really involved with it, I don't know if they could actually describe it any better than that. Maybe we can talk about that after. In terms of the problems, in the abstract, I alluded to this. This is the best way I can represent 50%, or half white, half red, half black, half blue. 50% of all energy use in Canada is attributed to the built environment. Buildings of all typologies, hospitals, hotels, institutional, residential, low-rise, high-rise. Just let this burn in your memory. And this shows up again. It's now under problems instead of driving factors. This is downtown Toronto. These glass condos, Ted Kessick, prof in architecture at U of T, was in the news lately, the condo conundrum. Well, it's not only the condo conundrum. Our buildings are are terrible. We build them terribly, you know, and that's the history of our construction and our design. For this presentation, I wanted to show another problem. The typical commercial envelope, as Tom alluded to, it is a low-hanging fruit, the commercial sector. And I Googled typical commercial envelope, and I found another problem. This is what came up, unbeknownst to me, right? And then I was like, how much? 26 pages of envelope specs with arrows and engineers, and it was the 27th page that I got to a building. And I was like, oh, wait a minute, it's not even on people's radar. Forget about it, right? The informed academic was like, should have said building envelope, but nobody's thinking about it. What can we do about that? It's a big problem. And we think about legislation. The building code, I tell my students, the building code represents a set of minimum prescribed requirements. Minimum prescribed requirements. However, the industry's flipped, and now it's looked at like this. And this is how we build. We kiss the building code. We kiss that minimum set of prescribed requirements. How did that happen? There's a fundamental flaw there. You know, the building departments, they have to issue a building permit if you hit the building code. So fundamentally, the codes are flawed in my mind. And then society as a whole. There's a lack of education. There's a lack of knowledge. How can you start to fix problems if you don't know what the problem is? I look at a building, be it a house or a hospital or whatever, I see bad windows. I see energy leaving and coming when you don't want it. I see air leakage. And someone else might look at the building, they see paint colors or nice stairs or nice columns, you know, architectural columns. It's just, it's a knowledge gap. And then there's expectations. Who are we to say, I want 23 degrees on the inside during winter and 21 degrees on the inside during summer? I mean, to me, that's just backwards. But it's about expectations. It's about what we expect and how we can sort of get into people's minds and break that down. And then we think about the economics. This is very brief, very back of the envelope, but my mom's Dutch. I'm Dutch, and we're known to be thrifty. So I was thinking, economically, let's think about the cost of generation. These are very broad numbers. But you start to look at, you know, nuclear, coal, you know, this is pretty low, but it doesn't even have carbon capture. Renewables, you know, when you're in the 2,000, 3,000, 4,000, 5,000, you kind of benchmark that against the cost of conservation, and you have what I'm talking about for these 15 minutes. These four elements, these four strategies, sealing ducts, you know, insulating attics, insulating basements, they represent about 40 to 60% of the capability, let's say, you know, of the possibilities. And we're talking 1,500, 1,500, 1,300, 2,000 versus minimum 2,000, right? It actually makes sense, as Tom was alluding to. It makes sense to conserve. And, well, it was a perfect segue, I said, Tom's presentation, Tom's chat. I'm going to give you 4 examples of technology, brief overview. Insulation, right? I don't care if it's mineral fiber, glass cellulose bats, extruded polystyrene insulation, expanded polystyrene, spray foam, cellulose, or ripped jeans, right? Cotton, doesn't matter. We're building 2012 code, it's about that, maybe a little bit less. We're building this thick, where we should be building this thick, somewhere around there. We're not using it right. It exists all around us. The insulation aisle at Home Depot or Lowe's, Rona, Canadian company. But we're not using it. Windows. If we look at the U value, which is essentially, here's a building science lecture in 30 seconds or less. The U value is heat transmission. It's energy through a square meter for a temperature difference. So if you draw a square meter and you just visualize this energy flowing through, how much energy is going to flow through that square meter for a 1 degree temperature difference, from 20 to 21. That's what I'm visualizing here. 2012 OBC, the Ontario Building Code, is considered aggressive, or it's a big step, people say. And the U value there is 2. One of my research houses, you know, I didn't go out of my way to get these windows, and the overall U value of the windows in my place is about 0.9. More or less the best in Canada right now. It's about 0.6, 0.65. And the passive house standard, which I'll allude to in a few minutes as well, it's a very aggressive low-energy building standard, started out of Germany, it's gone across Europe, and it's making headway in North America. We're talking 90% energy cuts here, very, very aggressive, where we have to be. You know, 0.5, 0.45-ish, right? A quarter of what we're doing right now. So the technology exists. It's off the shelf, but we're not utilizing it. And the third one, it's better in dark light. What you're looking at here is a big black box, so it's actually showing pretty well. It's a heat recovery ventilator in one of my research houses. It's actually an energy recovery ventilator. So if you know HRV, the H is for heat, that's just for dry heat. ERV, energy, that's for dry heat and wet heat, latent heat, sensible and latent. So what's happening here is you have house, fresh air supplied to the house, fresh stale air coming from the house, fresh air from outside, it's insulated because it's cold, and stale air going back to the outside. Now as a building scientist, I preach you need to tighten up your envelopes. You need to minimize the air leakage. You need to minimize the uncontrolled leakage of air because air represents something that has to be conditioned, which represents the use of energy. So as we tighten up our envelopes, we now die. We don't have any fresh air. So people figure that out, believe it or not, trial and error, sick building syndrome, and they said, oh, now we have to introduce fresh air. And so I go as a building scientist, tight, 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 tight. That's my camp. And then I say, why? Well, because then you could say, you know, fresh air, I want you to come through my building right here, right there, because I know you're not getting in anywhere else. You're going to come in right there. And not only that, I'm going to throw you through something that recovers energy. Aha, the technology exists. The reason there's all these wires, don't be afraid of that. That's just the researchers' reality. It's measuring everything. And just a couple of days ago, it was -3 outside, and I had stale air coming into my ERV at 20, 20 and a half, not 24. That's from the house. And then I had fresh air that was coming from outside through the ERV at about 19, 19 and a half. This puppy has about a 90 to 96% efficiency. That's wonderful. That's the E in ERV. HRV is 60, 70, 75%. The last technology, probably not many of you recognize this gentleman, but you probably have heard of Antoine Lavoisier. And if that doesn't ring a bell, matter cannot be created nor destroyed. That one kind of rings true, right? Conservation of mass and energy. Fine, I'll accept that. But as the engineer, we can manipulate the physics. What I'm showing you here is a heat pump. And heat pumps they take advantage of the vapor compression cycle. It's a whole other 5-hour lecture. Basically expansion and contraction. And they have efficiencies, COPs, coefficient of performances, of 3 or higher, which means efficiencies of 300%. Forget about the A+ of 100. 300% here. That means for every unit of work that goes in, you have 3 units coming out. And these things deliver heating and cooling. So we do have the technology. Tom alluded to the low-hanging fruit. To me, the thermostat. 3-4% back of the envelope right there. We lower the thermostat in the winter and raise it a bit in the summer. The AC, the ubiquitous central air conditioner. Most of my neighbors turn it on June 1st. They walk away and they turn it off September 15th. And it's about adaptation. It's about people expecting everything to be perfect. I argue that it's about living with the seasons. People think I'm crazy. I've actually had neighbors go up to a student that have done some research in the neighborhood go, oh, that's a professor in that house. Why are those always open in the summer? And I'm like, oh my goodness, this is what we're dealing with. Well, it's because most of the time it's comfortable. There's about, by my calculation, 2 to 3 weeks that you actually need the air conditioner. Obviously, this is augmented by the fact that the house I live in is well insulated, doesn't leak much, so I can smooth out those spikes in a hot day. You walk around in the summertime, after a hot day, it's 15 degrees in the morning. My wife doesn't take walks with me anymore because she just thinks I get angry. It's 15, you're cold, because it's the summer, and everywhere you look, you hear, and these central air units are pumping cool into the house. It just doesn't make sense. Turn off the lights. Well, that's straightforward. Look downtown at night. Kind of wonder, especially the office buildings. You go for the next 10%. Non-invasive air leakage mitigation. Okay, you get a blower door, you suck out air, you force the air leakage to happen, you go around with a lighter, you don't burn down your building, you find the leaks, and you fill them up. I show this to my students a lot. This is the grade everybody wants, right? There's no COPs of 3 in academics, right? That's what you want. Why don't we want that for our appliances? Why don't we want that for our combustion appliances? People still buy 80-85% efficient furnaces or something. You can get 90-96% efficient, 98% efficient boilers. I already alluded to 300% for heat pumps and that sort of thing. LED lighting. This picture shows a lot better on the screen, but this is my kitchen, and no flash. And what you're looking at is par 20 pot lights, as they're known at Home Depot, par 20 LED lamps, and they're nice. And people come into my house and they don't notice. They're good technology, and they operate at a fraction of a cost of incandescents. And then we go to the next 80. The next 80 or 90%, legislation. Every time I speak to somebody from government about, elevating the codes to the levels I want, they go, well, how can you do it? How is it possible? Show me some examples. And I go, okay, the Passive House standard. These are North American buildings built to the German Passive House standard, residential, commercial, that represent 90% energy savings. This is not a rendering. These are real buildings. It's done. We need built examples, but we need legislation to push forward. And then with legislation, you do need quite a bit of innovation. One of the research projects I'm working with right now is called the Gemini House. And it's, essentially, it's a house within a house, a box within a box, essentially, a core and a perimeter. And, it's not that separated from the outside. This is the south elevation. You still get sunlight. There's an actual blue buffer zone around everywhere here. What happens is when you have extreme hot or cold weather, you hunker down into the core, and we actually spend most of our time in the kitchen and living room, the bathroom anyway. And you say, oh, heat's going to be lost, but you put a heat pump in this perimeter, and you suck that back with efficiencies of 300 or 400% now because the temperature difference is not that bad. And voila, we have a project with U of T, a co-PI in mind, that we are tendering the demo as we speak. Actually, the meeting's right now. And so we have a built example. Obviously, it's easier from new construction, so we're taking on the most difficult thing. Other innovative approaches, preheating air or water, full mechanical systems that no bit of energy is wasted in these black boxes. If there's a little expelled here, well, I'm going to put it in the water here, and vice versa. The technology exists even though it's innovative. I want to conclude with the idea of what I think, from my perspective, what we need for the research. And first off is this idea of data, proof. We need proof. And I agree. I have students working with some residential passive house projects that are being built in the GTA, and we're looking at things like what happens when you go from this to this. The rules don't necessarily stay the same. Are we going to have condensation in the middle? But the only way you find out is 15 years later when your wood supports are rotten and the second floor is sitting on the first floor. We need proof. People are, I don't want to build that thick. It doesn't make sense. What's the hygrothermal realm? We need data. What's the energy savings? What's the comfort? What are the user perceptions? What is going on? It's the answer we need. The psychology of how people use the buildings is a very, very close to my heart subject. I have a PhD student working on the psychology of energy efficiency. My argument is, as you take the energy pie of a building and you shrink that using technology, everything I spoke about, the COP, the heat pump, and everything, you shrink it a little bit more. Eventually you get to a point where technology can't help you. Not that much. Right? Now it's about how the user drives the building. And if you're going to try to make that pie even smaller, you need to understand the user's perception. You need to understand their energy literacy. You need to understand their perception of energy efficiency measures and that sort of thing. So it's exciting research going on in that realm. I have another student looking at how do we build these things, right? How do we go from this to this? Not just draw it on a drawing and kind of use AutoCAD and go stretch another 6 inches. No, it has implications that have implications on structure, services, and everything else. So we need to quantify that. Cost. Well, sometimes I don't speak about cost. That's when I can jump to the academic side. But the reality is you need to. The idea here is that you need to speak about the real cost, life cycle cost, or even bigger picture, what the true cost of energy is, not just what you pay on your bill. So I have some students looking at that as well. Finally, I can sit here armed with all my solutions, right, the academic, and if I don't do the right implementation strategy, I'll be sitting here a very long time, very long time. So I have a student looking into how do we implement this? How do we get governments to adopt that? We need everything I've spoken about before we can actually push this forward and see, for me, what best thing that I could see is to elevate these codes right now. So my time is up, and went over everything broad level. If you have any questions, I implore you, please jot down my email and fire away. If there's no questions that are answered after here, I think we have a bit of time. Thank you very much. We got a few. Yeah. Yeah.
Actually, I want to clarify something first before I can ask my question.
Sure.
Do you use the heat pump as the only source of heating in your house?
My house is not the Gemini House. Are you referring to the Gemini House? There is, because the building department requires it, there is a heating system that provides the design amount of energy as the code says it should. That switch should remain off pretty much all the time.
Okay, but then my question is, if you have a heat pump that basically takes the heat out of the air,
Yeah.
how much energy, like,
Where does the energy come from?
well, yeah, I mean,
Yeah.
the pump needs electricity.
Yeah.
How much is that going to cost versus what you get back in terms of heat?
So the actual heat pump technology, so the question is how much, what's the implication of the electrical energy to run the heat pump? And I'll even further that with where does the heat come from after a certain point. The heat pump is such that, absolutely, I'm not saying we're running this thing for free. I said maybe simulation shows that we can cut our costs by 80% or our energy usage, our intensity. We do need electrical energy. But because it's a heat pump and we're taking advantage of that vapor compression cycle, for every unit of energy we purchase from the grid, we actually get 3 or even more units of energy delivered to our site. So we still have to use that unit of energy, but we get 3 or 4 to the site. Rather than a traditional furnace, say, it's, you use a unit of energy and you get maybe 0.95 of a unit of energy of heating or cooling or that sort of thing. So we take advantage of that. Where the heat comes from, there is some times that we're going to have to generate auxiliary heat to start up that core, basically. Like, how does it start? It just doesn't warm up. But then there's internal gains and that sort of thing that maintains the heat generation and solar gains and that sort of thing.
Okay, question at the back.
I'd just like to sort of make a comment. I'm an economist,
Yes.
and so I find it very sort of objectionable to sort of try social engineering. My idea is that we should have this technology and we should have the government legislate it. I would say that you're probably going to reach a wider audience if you just sort of stick to the great technology, your great research ideas, costing things out and just say, these are what's available, this is the cost advantage, and if there's a cost advantage, it'll sell itself. The average industrial wage is around $40,000. You're talking, when you're looking at real people, and you're putting high upfront costs to them, it's not going to work. It's going to cause economic disruption. So it will sell itself if it's cost effective and it's good. And I think if you stick to that neutral, that engineering approach, that's what I would suggest would work. Certainly you can twist some politicians, and I've been in government and I can see it, you get a nice hot idea and they'll run away with it without doing appropriate economic analysis. But that isn't good for society either. Your engineering solutions, if they're good, they will sell, with that, all by themselves, with cost.
Yeah, and it's an excellent comment. I don't disagree, but my belief is that solid engineering solutions will only get you part of the way. And that part of the way, statistically, is not enough. That's my problem. I can sit in the engineering field and just do that, but we need to get further. And so how do we do that? And that's where the psychology of energy efficiency points in. In terms of capital cost, I truly agree with you, but I was making allusions to legislation. And yeah, I only have 15 minutes to chat, but legislation has to be not only to elevate the codes, I'm not saying offset the capital cost to the average wage earner. There has to be other programs to offset that capital cost. Remember, it takes less cost to conserve than it does to generate. Okay.
I'd like to comment on this. I mean, the way it works, usually you have trade-offs. So if you spend more investment and more money in your building envelope, you don't need as big of an air conditioning unit. So you take that amount of money that you want to spend in your air conditioning unit and invest it in the building envelope. But you're at the bigger picture, you're consuming less electricity and less gas. So that's. But the problem is there's a disconnect in the design process. So the building envelope engineer will try to invest in a bigger, better envelope, but the mechanical electrical engineers don't know what's going on with the envelope, and they design the air conditioning unit that they usually do. So, yes.
It's not easy, that's for sure.
It's about changing how we do things. That's pretty much where it is.
Okay, another question back there? Yep.
So at one point earlier on, you mentioned turning down the thermostat as low-hanging fruit.
Yes.
And I have trouble believing that that's low-hanging fruit because I don't see any low-hanging obstacles to that. I think if that were easy, it would have been done. I actually would suggest that that's an extremely difficult thing to achieve, to change public perceptions, and to, what you're really talking about is influence a large majority of the public to give up a little bit of what they perceive to be their comfort. And with lighting, that may be different, but with things like turning on the air conditioning and or not turning it on, or having to do more work, or having to be how they perceive to be less comfort, I would suggest that that's actually very high fruit. And achieving that is not something that I think the technical innovation that you have shown in a lot of these areas, a lot of these technologies, is actually a lot easier to bring to market than changing the way the public use their own thermostats.
Fair enough. The economists proved us wrong, such that the capital cost is a huge barrier. And yeah, it's not going to be, we're going to go into everybody's house and just lower the thermostat by a degree. But there have been numerous studies, and there are utilities that actually control combustion appliances, such that, you know, a single degree, people don't really notice it. And yeah, I can't sit up here and give you the exact scientific studies, but I can show you that at least 50 people that I've influenced over the past 2 years, small sample set, they don't. It's about adaptation. And I'm not saying cut it 5 degrees. Yeah, we're gonna notice. But if you take it from 22 to 21, most people, they need a little bit of motivation, yeah. They're not gonna notice anymore. That's my belief. So, you know, we can respectfully agree.
Question here?
I just have one more comment to the lady that spoke earlier. I don't necessarily agree with your view, because the problem is that there are different interests, and the developer that just builds the house and then sells it doesn't care how much the house later costs in energy. So unless the consumer actually demands that the house conserves energy and saves him money, why would the developer build it that way? So the codes would actually help and kind of force the first person in the first place to build the houses that make sense for the consumer afterwards.
There's one more question at the back there.
I guess it's a bit of a comment as well to the public perception or changing public perceptions.
Yep.
I've worked, like pushing the Peak Saver program to the public, and I find that when you tell the public, you know, this can help prevent a blackout like 2003, or perhaps prevent building another expensive nuclear power plant, it's enough incentive to get the public to make a little small change. So I'd say there is opportunity in making those public changes.
Small changes.
Small
How many
changes.
people down here know Peak Saver? Anthony here? It's working. Yeah. Didn't expect you to. It's fine. All right.
Thank you very much. Or one more?
Oh, one more.
It's up to you.
Oh,
Oh, okay, two more.
I have one other thing to add to that. The regulation and rent control, for example, where the building owner wants to put in individual metering for master metering and make the residents responsible. They have an interest in keeping capital costs low, as the previous commenter said, and then put the burden of the operating costs on the tenant. So there is regulation in effect in that kind of environment, and the same thing is true when the builder is building a subdivision. They want to have the lowest price house to sell, and they can't. It's very hard. I mean, it's done a little bit. It's very hard for a builder to sell an energy efficiency house that costs more. Go ahead. You used as a benchmark the 2012 Ontario Building Code, which for the first time includes energy modeling requirements in Section 3 for single-family dwellings and upgrades in Section 9 for commercial buildings, higher level of modeling, which will provide the type of data that you referred to.
Yes.
What type of impact do you see those changes in the building code having on the design of buildings that are currently in the channel?
Okay, so how do the changes from 06 to 12 perhaps set the path of the future? Excellent question. I didn't want to get up here and slam the 2012 code, and I think personally I did a good job of not doing that. It's made an advance. I just don't think it's where it should be. So I think, you know, the idea of modeling and informing the design earlier as a prescribed requirement is a good idea, and it's definitely heading in the right direction. I think once people get over the, oh, really, you know, sort of thing, it's gonna actually start to snowball. The one perhaps caveat to that is that there's this set of 12 or 13 prescribed packages to, you know, for Part 9 example. If you do A through X, good, you don't need energy modeling. If, you know, and that happens 13 or 14 times over. And the problem I have with that is that it takes certain things. The insulation can go up and down a bit, you know, correspondingly if your heating appliance efficiency goes up and down. So it's trading off. And I know I have an idea why they did it, because they're starting to give options and they're starting to address. But I hope in the future they take that compliance package and clamp it down and say, you know, these are the levels. No trading off this and trading off that. You know, in fact, these are the levels and a bit more and so forth. And I think modeling is going to inform that for sure. So it's good on them.
Very good.
Thank you.
Thank you, Russell. Yeah, very good. I'm going to move on to Farid Bensebaa, and he's a project leader at the National Research Council of Canada since 97. He's with the Department of Electrical Engineering at University of Sherbrooke and is an adjunct professor with me at York University. We share an office, but I don't see you up there very much. I know you do a lot of traveling, and I know your specialties include nanotechnology, solar energy, fuel cells, and distributed power generation. So, Farid.
I guess right now one of the issues now is how to address this issue related to long-hanging fruit. I'm sad to say this, but in some, particularly for solar thermal, they tend to produce the start of fossil fuel, building large power plants. Although this is good, but I think we need a lot of technology development to address the current issues. And right now, you have this people are talking about technology push. Basically, I have a technology. That's what the lady's saying. You have a technology, go forward and sell it. But there's also people saying we have current market needs. Then you have to address this challenging issue. This is why you have these people putting one direction and other people putting the other direction. I guess if you don't look at the blue part of the picture, you may see that this is like a fossil power plant. Actually, this is a solar power plant. It's what's called the solar thermal power plant. And 5 to 20 megawatts. Then you need basically to do this. You need to build the grid. I guess you all heard about this Desertec project, where you can build a large solar power plant, build the grid, transport energy to Europe. Actually, there's no grid to do that. And if you want to build that grid, I don't think you will build it in the next 5 or 10 years, at least. For those people actually who knows me, I guess I was involved about the IEA task force. I agree with a comment from Tom Rand. It's a very, very conservative agency. And for them, solar technology, it's about building this type of a plant. We talk about basically about comparing solar technologies to nuclear. We heard that nuclear a lot, but it's a very cheap. You always have these numbers, which is basically $1 a watt. Actually, the reality, it costs mostly more than 10 times that. Why this difference? Some people say the hidden cost. Other people say that it's a lie. It's actually a combination of the two. You never see, when you build a solar, a greenhouse PV rooftop, you never heard someone paying more when they had to pay from the beginning. If you have a bill, it's good. You have to pay this, then what are you going to end up paying? In nuclear plant, it's always 2, 3, 4 times more expensive. This is a hidden cost. And there's also what calls, for example, one of the things that's very often happens in these nuclear power plants, it's the comparison. It's very difficult to compare. This is calculation made by a group in the United States. Actually, right now, if you really compare the two, although it's very difficult, actually the cost, it's about the same. I'm not talking about capital cost, the cost of electricity. But the reality, it's very difficult to compare. One of the actually, Russell mentioned that why we don't shut off the light during the night. Because if you had to shut off all the light during the night, you had to shut off those nuclear plants. And you cannot do it. because the calculation often is made based on the what we call base load versus peak load. This is why it's always very difficult, I would say, to do the comparison. And smart grid, although I'm not an expert in smart grid, it's basically going to help basically integrate this distributed. I'm talking about distributed power technologies. This is your spaghetti. Although this probably is a little bit clearer. Then basically the challenge, how to integrate those technologies within a urban environment. There are current technologies that can address this building integration projects. You have on the right side here, basically using just current solar technology, crystalline by solar technology. Basically, you can combine power technology and also having a light. You can do it by just spacing the solar cell when you're building the solar cells. Or you can basically using also what current thin film. But they both have challenges. The biggest challenge basically now, the biggest challenge of this technology, they're either very heavy in case of crystalline silicon, then you have to basically use glass, or in the case of thin film, which are most flexible, the efficiency is very low. The area, you don't have enough area to basically cover your needs in terms of energy. Then basically, those are the two issues. Most of the technology you had was amorphous silicon. It can make flexible solar panels. You can integrate them in any shape, but the problem it's a very low efficiency. And for each kilowatt, you need at least 15 square meters. You have this crystalline silicon, which is high efficiency, but it's very difficult to do the integration. Okay, this is basically what I'm trying to sell you. There's a technology called 6. It stands for copper indium gallium selenide. Basically, it has both work. It's high efficiency, and also you can build it in a flexible substrate. You can actually, there's a group in Switzerland, they reached actually a 17.6% efficiency on a flexible substrate. But there's a catch on this. It's expensive, and the energy input, if you look at the life cycle analysis for the people who know this, it's relatively high, because basically they use in making those thin film, they use quite energy intensive technologies. At the National Risk Council, we had the technology, and for actually one way how I met Jose, because I was going around probably in the Toronto area, trying to find actually investors to basically take this technology to the next step. And the best investor I found, I said, okay, I can give you 6 months to develop me this technology. I said, no way, you're joking now. But anyway, at this time now, it's still, the technology is there. We have patents, and it's still not yet developed at the commercial stage. Then this is basically, it's a follow-up pattern. It's basically how to make, it's explain how to make this flexible substrate based on these materials. Yeah, I think it's basically, it's in case of photovoltaic, what the message I'm trying to say is the technology is there. It's not a question, basically, it's developing them further and integrate them to address the issue of BIPV. It's not saying that I'm trying just to pitch for my technology. I think it's for the people saying that PV takes in a lot of place. There is this technology from this a Canadian company. I guess you all heard this light thing system based on LED, which is powered by PV. They always have this large solar panel on top of the pole. Actually, they have this very bright idea. What they did, actually, they're using the surface. I don't know if you see it very well. You see the surface along the pole. Basically, instead of buying those solar panel from the market, basically they built that small solar panel there. And here, I think they remember. I don't know if they have the number here. I know that it has something the equivalent of at least 10 or 20 kilowatt along the surface of the panel. And it's very, very beautiful. This is basically they're using it on near the highways where they can light the pole. And this solution actually they can be used for both off-grid and on-grid application. I'm going to switch to the next topic with the solar thermal application, just to provide you with one example. I guess everybody knows in Toronto about the solar wall, where they use basically solar thermal to produce heat. In theory, also we can use this heat also to cool the building. It's a worldwide known company, and everybody knows also about the using also solar to heat the water, which is on the right side. Right now, one of the biggest challenges of this of the solar thermal is low efficiency. As here, for example, just to address the market, in this case, they use very, very low efficiency heating system, absorber system, and basically then this is why most often this is you see it just on large commercial building when you need a lot of surface area. You do have a lot actually technologies where you can actually use smaller surface areas. This is one challenge of the efficiency, and the second challenge actually flexibility of the substrate. In collaboration between NRC and York University and also the a university in Belgium, we actually embarked in developing a new technology, developing a technology that allows you to have high efficiency on flexible substrate. And here basically just show you, and the goal basically to have this technology operate at high temperature, around 200 degrees C. As you can see, in current technology, usually efficiency, when you operate high temperature, it tends to have a lower efficiency, and also there's also an issue with degradation. Basically, then you have two. Right now in the market, you have two technologies. One, high efficiency, very expensive, and low efficiency and cheap. And what we're targeting now basically something intermediate between the two. And flexible also. You do have, for example, this is a very good technology from, it's a German company, where actually it can obtain a very high efficiency. It's called TNOx, basically titanium nitride coating, where you can have very, very high efficiency, but unfortunately the cost it's quite high. And also they have issue with degradation at high temperature. We, in our case, basically, as I mentioned by Peter, what we're trying to do, use nanotechnology, and we use a technique called electrophoretic deposition. We can deposit this material on any surface. And we did it with using nickel nanoparticles on aluminum substrate. We can do it on other substrate, and the processing is at room temperature. You don't need any vacuum system, and we did it also in collaboration with Valley Inco. And the only restriction is basically you need access to this high value material. And Inco is one of the few companies who actually developed this technology. And unfortunately, they stopped doing it because they didn't find market for their material so far. And thank you. I just hope that I showed you that there are current technology, photovoltaic, solar thermal on flexible substrate. And as I mentioned in the case also of the application, the policy needs some improvement to adapt to the current needs. Thank you very much.
Thanks, Farid. I was very intrigued by your slide that had that mapped out coefficiency of it's actually that one of performance versus temperature. And like many graphs I've seen of this type, it starts at 0 degrees Celsius. My question is about applications, since you work for NRC. In Canada's far north, which obviously the temperatures are far lower than 0 degrees in the winter, and even in the summer. In the winter, there's very little sunshine. In the summer, there's almost 24 hours in many cases. What if you could extend that graph backwards? What type of efficiencies would you see at -20, -30, -40 degrees?
I should tell you this work was originally done by actually a group in Sweden, because this is why actually they have the same needs as in Canada, but they have. This is why you need one of the needs. You need to have high efficiency, because this is why actually they have a need for this. Yeah, and we didn't do that calculation, but in this type you have to be careful now. We're not. This is temperature. It's the receiver temperature. It's not actually the outside temperature. It's because basically there's a difference there. Because why it's important is a receiver, because basically the material properties are changing as a function of the receiver, basically the thin film depositing. Yeah, I think it's. I didn't do it specifically. We can do the calculation versus the ambient temperature, but I didn't do the calculus. We can certainly do that.
Those numbers are available for a project that I'm currently working on. Far north, I appreciate.
Because we have now a model. I can send you the Excel model. The student, what we did, he did actually we developed the Excel model. We can share that. No problem.
Okay.
A lot of the precious metals that go into the SIG cycle panels, you mentioned Vail, they're typically the byproducts of mining, correct?
Yes.
So a big part of the problem is that there's no market to directly mine these materials. When in the future do you predict that market might be there? How long might it take to get to that point?
You talking about market for the metal or for the product?
For the precious metals. Yeah.
Okay. Actually, for this one, for the 6, well, actually, because this is why I was surprised they couldn't get any driving in this project, because one of the company I was behind it, it's a Canadian company. It's what's called a producer based in Vancouver. What's called they're producing nickel. Basically, for the case of selenium, which is most actually people talk about about indium. Like the most expensive one is selenium, and selenium is a byproduct, as you said, of copper production. They said you can provide you with the selenium, and you can provide you also with the indium. Yeah, I think it's a lot of people saying that's the drawback of this technology. Talking with this mining company, I forgot the name. Okay. They said it's not a big problem. Because what happens, the indium now, it's the driving force for the indium. It's not the iron now; it's the PV. It's actually the flat skin market, because they're using the indium for the what's called the TCO cotton glass. And what they do, the markets react very quick to that. What they're doing now, most of the glass now, it's recycled to remove the indium from the glass. The recycling now, it's taking care of the higher demand in this market.
Back.
I want to make a small comment. I liked your slide at the beginning, talking about putting the big solar projects that need greater development. This is sort of commenting basically on that line. I think one of the costs of solar or is the grid here, and the sort of the distributed costing costs. It's a hidden cost. For instance, looking at smart meters cost us $1 billion. The hidden cost of distributed energy, whether solar or wind, is something $8 billion or whatever. That's that we don't see. So when you're comparing nuclear to sort of distributed solar, you actually have to take those distribution costs into account as well. So I like your idea, or I like that doing more the self-contained, the smaller units is probably wonderful and more viable and so on. So,
actually, it's even worse what you said. Actually, there's a distribution. What I was talking here in the case of the desert, actually, it's transmission. Actually, getting this distribution. Yeah, that's right. Yeah, that's distribution on the transmission. That's correct.
Any questions? Great. Thank you very much. Very good. I'll just make a comment if I can, and really interesting to hear Farid's background, and it's great to see the research being done. Interesting question about the smart grid and who should bear the cost of it. To me, one of the major features of Ontario's commitment to the smart grid is the ability to use time of use rates so that people in their homes do no longer have to pay a fixed price. That there is, because our electricity generation system, especially in Ontario where we have different types of generation, some very, very cheap, Niagara Falls, some very, very expensive. And without the smart grid, there was no opportunity to give people the price signal that 2 o'clock on a hot Thursday afternoon, electricity is more expensive than that same day at 10 o'clock or in October in the middle of the day. So we now were able to send those price signals to consumers at their home and offices. And I think so. That's one of the. So it's not just the smart grid in Ontario and the smart meters were not done just for solar and renewable. I think they've got many other features to them, and I think the largest is the opportunity to send demand response signals to people and have them react in their homes and in their offices and in their factories to this real-time pricing of electricity. But anyway, very good. I'm glad you're joining the conversation, and thank you for your questions. And from the economics point of view, it's interesting. We're now going to move into the international part. Oh.
If you want to reduce your energy consumption level and improve your energy efficiency level by 2020 on a 20%, and one of the measures that is going to help with that is not going to be fully in place till 2015. Are you going to reach that target in 5 years? That's my question. Something else that is being done for the building sector at EU level is, instead of with regulation as a voluntary approach, there is the Green Building Program, and it's sponsored by the Commission, started in 2005. And this is specific for non-residential buildings on a voluntary basis. And the signatories, or the people who want to participate in this program, should try to reach an energy consumption reduction by approximately 25%. I'm listing here the countries participating in this initiative so far, and as you can see, not all the member states are here. So, as a big difference between mandatory, not mandatory. If you put something that is on a voluntary basis, you're going to have some countries out of the initiative. So my view will be that you need both things, regulation and voluntary approaches. And just some conclusion. The energy sector has been considered, but not now, years ago, as key to get out of the crisis. The energy efficiency goal is the one that probably won't be reached. building is the sector where energy saving and energy efficiency measures are far from being fully implemented. So there's much more to be done. And for me, what is annoying really is that all these time frames and delays for implementing these measures. So right now, the EU has a strategy, a roadmap to be a low-carbon economy by 2050. So maybe when they are talking about goals for 2020, they think it's not important if there is a delay and the goals are reached by 2050. And that's something to worry about. And that's all from me. Thanks. Specifically for the building sector or in general?
Just in general, what is their perception? What is their view on this?
The perception is, in general, that the measures are being taken late all the time. The Commission conducts a series of surveys to know what the public is thinking of. And everybody is happy to have all these measures implemented. As long as they don't cost too much. That's the big issue all the time. But they are willing to implement them. There are differences between each member state, and it depends on how strong is, for instance, the green parties in the country. For instance, in Germany, it's much stronger than in Spain. But in general, all these measures are accepted. They are perceived as very costly, that's true, but the measures are accepted. And the particular case of Spain is a bit different because the high unemployment rate is a barrier right now for implementation of something new that could mean closure of existing buildings or existing, for instance, nuclear power stations and things like that. So it mainly depends on each country situation, but in general they are accepted measures.
Isn't this also seen as a potential to create jobs that we're having the same, I mean, every recent grad, so I know this person is having the same issue here, we're saying job creation. Are you guys better off there?
Well, Spain, there are many reports in the case of Spain indicating that developing to the full the potential of the renewable energy sector or the green job sector as a whole will create more employment in Spain than in any other member state. We are talking about 700,000 employments over the next years. The issue right now is that there are so many budget constraints to implement some of the measures that there have been a lot of delays in approving the transposition of the EU regulation. Hopefully, something will be done.
Question back there?
Are green roofs popular in Europe as a measure of energy efficiency?
Sorry, I couldn't hear you.
Green roofs?
Green?
Roofs?
Small ones. Very small ones. One thing that has changed, if you have seen, I don't know if it has arrived to the news in Canada, is something similar to what's happening in the States. The Occupy movement started in Spain, started in Madrid. So there are a lot of people that have joined this movement, but because they have decided not to be a political party, they have very low representation. For the first time in the last elections in November, one group related to this movement in some sense, I mean not fully, got parliamentary representation, and he was formerly the president of Greenpeace in Spain, if it means something.
What I meant was like on a house was a roof, like green roof.
Oh, sorry, I understood green roof. Sorry.
That's okay.
Yeah, many. One of the things that has been happening in Spain is that that's why we were known at the beginning, because we have a regulation in favor of renewables, very strong, feed-in tariffs and prime system and everything. So everybody wanted to have some farm in their gardens and things like that. So the whole country is full of them. And the regulation changed in a sense because we had so many of them that the government reached the goal it has established in terms of power installed like 3 or 4 years ahead of plan. So they changed the regulation.
So sorry, I think he's talking to, it's a green roof. Like where you grow plants on the top of a building? Yeah.
Yes.
Yeah.
Oh, okay.
So plants on top of a building, it reduces the heating and absorbs water?
There are projects, but very small ones, and nothing, for instance, sponsored by the public, just private initiatives at very small level.
Good.
What we have is sun farms in the roofs.
I guess you sort of started answering my question. My question is about the FIT review that happened, and you reduced the feed-in tariff for solar specifically in Spain, and that created a lot of problems in the solar industry.
Yeah.
And how did that affect the employment in that? You're saying that, you know, the potential for employment is so much in Spain. How did that affect employment when you reduced your feed-in tariff?
When the feed-in tariff was reduced, first it was for the solar sector, but then for the whole, I mean, for the wind sector as well. The effects over employment hasn't been seen so far yet because this was the last regulation, and the reason to reduce or eliminate fully the feed-in tariffs was because of the huge debt. So it's something very recent. What they did before that was to change the regulation, and once the goal for solar energy installation was reached at a certain level, they decided to decrease the subsidies and prime system. And what they did it was to change and give priority to the projects that instead of being sun farms were installations in buildings. But it's overemployment. I mean, we have almost 20% unemployment rate right now. What we have seen is big energy companies canceling some of the projects. But as they were so far planned projects, the accountability in terms of employment hasn't been calculated yet.
Great, thank you.
I think there was
another question, yeah.
I'm not up to date on this, so not going to say, but in terms of employment, the last economic study that I heard of, and that's also in the Canadian press at the moment, was that in terms of employment in Spain, one job gained in the green sector and 2.5 jobs lost elsewhere. So I think it's, I can you know, certainly if you look that up, you can see those economic studies. So it's easy to say what's going to be gained, but you also have to subtract what's going to be lost. So I mean, are they able to do that?
Yeah, definitely. There are studies pointing out that there will be losses of employment, but the studies have already calculated that the gains of employment are going to be more than the losses. At least the data I'm
Jose,
yeah, what I wanted to say, I think the report that you mentioned, it's been on the Canadian press on the last month or so, and it was from a professor on a university in Spain. This was a report that has been very widely discredited because of the rigor that this person applied to do this study. And I wanted to highlight, if it's the same that we're talking about, there is debunking that's been done by a number of large organizations such as the National Renewable Energy Laboratories, the International Feed-in Tariff Corporation, etc. It's been widely discredited. And what I wanted to highlight to people is that the countries of Spain, Germany, now Greece and Slovenia have a group called the International Feed-in Tariff Corporation. So it's a governmental group, an official governmental group, and they're meeting in Athens, Greece, today, as a matter of fact. In fact, I was supposed to be in Athens, and instead I'm in Toronto. And the point of the story is that if you Google International Feed-in Tariff Corporation, you will see the PowerPoints that will be placed today very soon. And they do studies on behalf of all those governments, official studies on employment creation. And you can go to the previous workshops that they've held in Brussels and in Berlin and in Madrid. And all the data is there. You can see it yourself. And in particular, I want to highlight the German studies on renewable energy creation, because they are the most sophisticated ones. They take into acquaintance net employment creation. So they look at the industries that renewable energy has affected, particularly related industries like nuclear power, coal, etc., to arrive at net employment creation estimates. And it's all in this website that I mentioned to you, the International Feed-in Tariff Corporation.
All right, maybe we'll put that website as a link to this, this seminar, this workshop. Thank you very much. Great. So I think Jose's discussion about Germany is a great segue into our next speaker. And I should also just say it's interesting, and this is a story that, you know, I think it's public enough, I'll share it with you, that in the Ontario government, when a few days after George Smitherman was appointed Minister of Energy, he went to a conference. And usually when a minister is just a new portfolio, it's at least a month, sometimes 2 months, where they just don't say a word. But that, if you know Minister Smitherman, now George, you know that's not the way he operates. And he went to a conference on wind, a Canadian Wind Energy conference in Kingston. And Jose, the bright young person he is, introduced himself to the minister and congratulated him and said, you know, you really should go to Europe to see renewable energy. You really know, you need to go to Spain and Germany and Denmark. And the minister, instead of sort of referring to his aides or mumbling or deferring it, said, that's a good idea. And so Jose went with Minister Smitherman, did their summer trip to the Germany and Spain and Denmark, saw it and came back. And instead of being briefed by people in the government, you know, deputy ministers and assistant deputy ministers and directors and presidents of this and that and the other thing, George Smitherman came back and said to those people, I've been there. Have you? No? Okay. Well, I've been there. That's what I want. I want an act that will bring a feed-in tariff to Ontario. I know you've got all sorts of problems with it. That's what we're going to do. At the same time, he also went to California and saw what conservation looks like in California. So he was able to bring that into his Green Energy Act. So I think it was a great example of leadership by Minister Smitherman, but also of Jose to seize an opportunity and to get someone, and again, Minister Smitherman, he's a very hands-on guy. He wants to see it. He wants to look in your eye. And all these talks about studies were not enough for him. He wanted to actually go, and he saw it. And it was a huge impact when he went back to the ministry and said, this is what we're doing. I've been there. You got questions? Talk to these people in Europe because they've done it, and I want to do it better than they did, but I want to learn from what they did. Yeah.
The story did not end there. The Electricity Distributors Association, which is the organization in Ontario that includes all the local distribution companies of electricity in this province, asked that they also wanted to do a fact-finding mission. This is what these things are called, fact-finding missions. And 12 CEOs of local distribution companies went to find out by themselves what actually it means to move from being simply a distributor of electricity to actually getting involved on things like renewable energy, energy efficiency, combined heat and power, district energy. And if you go to the website of the Electricity Distributors Association, there is a film about 17 minutes that explains the knowledge that was gained there. Okay, it's not an Oscar-winning film, but it puts into 17 minutes what it actually needs to have a smart electricity distribution strategy. You may want to look at that. It's in the internet.
Now, talking about Oscar-winning films, this session is being recorded. I expect to see our friend here in Hollywood next year and accepting the award for Best Documentary Film, but we'll leave that up to the Academy. But, yeah. We're going to have a half hour to debate that, and the role of government in all this, I think, we can spend more than a half hour on that one, that's for sure. Anyway, I'd like to move into our keynote address now, and we're very pleased to have Dr. Ursula Eicher with us. She's a physicist and carries out international research projects on solar cooling, heating, electricity production, and energy efficiency at the Stuttgart University of Applied Sciences. Published over 25 peer-reviewed papers and 3 books, as well as 150 conference paper. We're delighted to have you here and welcome, and we're looking forward to your comments. Thank you.
Thank you very much for the introduction. Well, when I thought about this topic of smart grids, that was this seminar's title, I thought it's a bit of a pity that we always just talk about electricity. And in Europe, it's the same thing. Smart grids automatically are associated with electricity, production, distribution, renewable electricity, and so on. And I thought it would be a good idea to get the focus a bit back on the heating and cooling sector, because in buildings, as you heard, we are mainly talking about heat energy consumption. And to sort of convert electricity via heat pumps back to heat is a story, but I think renewable heat, solar thermal, we heard about that as well, is very interesting also to look at in terms of smart networks. We have also electronic meters for heat. We can do demand-side management. We can even use network-based distribution to do demand-side management with electricity, because if you have electricity and heat pumps, you still need storage. I mean, if we go to this 100% renewable future, and everybody knows that electrical storage is very expensive, so why not use a heat pump and store the heat in a tank, which is very cheap? So we have this big debate of what is the best solution to manage storage, to manage demand. And one thing is for sure, we need networks. And we have an electricity network. I think that's a big advantage. We have not that many heating networks, and I'm going to talk about this. And you see the logos here on the top. We are actually in a very fortunate situation that although we have a conservative government, they decided to get out of nuclear after the Fukushima event. And they have now a renewable energy strategy, which is very heavily funding research. And these programs, the Energy Efficient City, NF-Stadt, and the Energy Efficient Heat sector is a new funding program where demonstration projects are installed in city quarters, to show what is possible not on an entire city level, but at least on a city quarter level, and both for the building efficiency and the heat supply. And this energy research budget got increased this year by 75%, and they want to go to 1 billion euros funding just for energy research. It's an excellent situation, so we can do many projects, and I tell you of one project we're currently doing in this program. Okay, Rosa has already explained a bit what the situation is in Europe. Here are the targets again for electricity and renewable in total. And you see the electricity targets, and that's obviously sort of electricity domination is quite high, 35% in 2020. And you see the renewable total of the total energy consumption is below 20%. And that's due to quite a weak performance in the heating sector. So there's not so much renewable heat around. And if you look at the top line on the right, 90% of our renewable heat in Germany is biomass. And you know, Germany is a very densely populated country. We don't have that much biomass. I mean, we still have some food production. Biomass is very scarce. But this is the only technology which is today really economically feasible. So biomass plants work, they are cheap, and that's what's done. Solar thermal is sort of on the brink of economic performance, but not quite there. So this is certainly a problem. We don't have the biomass, and it cannot be the solution for everybody. So the heating sector is quite weak in renewables, and the transport sector is a catastrophe. We have hardly any renewables in the transport sector. That's why the overall figures are much lower than the figures we have for electricity, 35%. And Germany is going to reach the 35% by 2020. Also the renewable target, the total target, the current projection is that we will have 19.5%, nearly 20%. So I think the short-term goals are very realistic, at least for Germany, for the richer countries, let's say. The long-term figures are much more difficult, also from a technology point of view, because if you go to 80% renewable electricity or even 60% total, you really need to talk about storage and demand-side management. And if you think of solar thermal in individual buildings, the water heaters, they cover maybe 10% of your heating demand. And we put a bit more surface area, maybe 20 square meter for a residential building, and then you cover maybe 20%. You support the heating system, but we have still quite low solar fractions, 20%. How do you get to 60 or 80%? This won't work, in my view, on individual buildings, because then we're talking about seasonal storage to shift the solar heat from summer to winter. And we have these projects, but it means even for a passive standard building, a 10 cubic meter storage tank. And you build your house around the storage tank. It's a bit strange. So that's why I think we need to go for networks that you can, if somebody injects solar heat, maybe the other can take it. So it's very important feature. Okay, we also see that the building rehabilitation rates are very slow. We have now 1.5% in Germany. I think all over Europe, we're talking about building rehabilitation rates of 1 to 2% a year. So that means we still need 50 to 100 years to get our building stock rehabilitated. And the first speaker, that's why I asked, I think it's very critical how this is financed and whether we can accelerate these rates. They didn't get accelerated over the last years, and the new regulations just always talk about new buildings. I mean, but new buildings are not our problem. Okay, and I think I will start with a very general problem that we have when we talk about district heating networks. We have rehabilitation, is quite slow, but the heat demand is going down. And if we talk about new districts, they have very low heat demand. Many districts use passive standard or low energy standard, so the demand goes down. But the infrastructure investment for the network is more or less the same. So it's very difficult for energy supply companies to build new networks with demand continually going down. And that's a big issue. And I will talk about this then while I talk about the renewable integration into the networks. I mentioned this funding program, Energy Efficient Cities. There are many projects of very similar scope to improve efficiency and to bring in renewables. And we are currently working on a project in Ludwigsburg. It's a small town with 100,000 inhabitants, more or less, north of Stuttgart. But all these projects are very similar. Mainly we talk about network-based distribution of heat. And here's a city which has some old parts and some new extensions. And the big fuss word now is low exergy networks. So which basically means low temperature networks. So if we have, for example, deep geothermal energy, we have a project in Munich, comes out with 90 degrees, you supply your existing city quarter, which needs these high temperatures, then you go to a new building quarter, and they maybe have floor heating systems, and they can get by with 30 degrees. So you try to cascade the temperature levels, a bit the same like in electricity networks. You have different voltage levels. In heat, we also need to think of having maybe different temperature levels to to adapt better to the demand and to make the network more efficient, because that means for a given mass flow, you can use the energy much more efficiently. Okay, sorry, this is in German. This slide, it's a study from the Central Ministry of Environment, basically showing that all the scenarios with very high renewable fractions in 2050 require networks for heat distribution. And we're talking about 60% of all the heat that will be used, these are the projections, should be distributed by networks. And if you look at today's situation, I mean, Germany is also a homeowner country. We have, everybody wants his own individual heating system in their basement. 85% are individual systems, and only 14% are networks. And that's quite a big challenge. I mean, if you think of building district heating networks, you really need to dig up all the streets, you need to put the pipes in, and to go to 60% will be a big challenge. And I don't know whether it will happen, because it might be that we go completely electric, produce renewable electricity, and then use heat pumps for efficient conversion to heat again. It's a bit of an open question, but I think we will still have some biomass, we will still have some cogeneration in 2050, so networks remain important. And you see the renewable mix is quite, there's some, the yellow one is solar heating, there's some deep geothermal, there's still some biomass used, and the rest is probably still going to be fossil. So I mentioned the problem. We analyzed this existing city quarter in Ludwigsburg with the current building stock. The existing buildings in Germany have typical heat consumption levels of 150 kilowatt hours per square meter and year. Then there are some of them are already now more efficient. And then if you assume a refurbishment rate of 2% a year, then you see by 2050, we bring down the overall consumption by factor 3, more or less. So this will happen even at reasonably low refurbishment rates of 2% a year. So we want the networks, but we know the demand is going down. And if you look at the, this is also in German, if you look at the network thermal losses as a function of the reduction of heat, so you have a given network, you reduce the demand, and that means for the given network your losses, your thermal losses increase. And we're talking not about marginal increases. If your heat demand reduces by 70%, then you'll be talking about heat losses in the network of nearly 50%. So that is very significant. And that's why it's important to bring down temperature levels or maybe increase insulation. So what are the solutions? Obviously, the solution also for networks is to insulate well. But it's a cost issue, and the industry doesn't want to insulate as much as the scientists would recommend. But there are obviously there are now many networks built with sort of more efficient insulation systems, these twin tube systems, and we can, just by better insulation, easily decrease the heat losses in the network of 30 to 45%. And also it's cheaper, because if you go for this twin pipe system, you need less space, it's easier to connect, and so on. Then there's also some technologies, developments of using new filling materials, which again have lower heat conductivity, with the same aim to reduce the heat loss from the network. And then one issue which is now very heavily discussed is, especially for new city quarter developments, is very low energy standards. I mean, conventionally, if you build a heating network, you more or less connect every building with your own heat transfer station. So the red dots are the substations, and they're not cheap. I mean, they have heat exchangers, they've got pumps, controls. Now, the more intelligent ones have electronic meters. Heat meters are much more expensive than electricity meters, and we're talking about investments of 6,000 to 10,000 euro, or Canadian dollars, more or less the same. So it's actually quite expensive. That's more expensive than a condensing boiler. And if you then talk about a passive standard building with a very low total heat demand, it never pays back. So we need new solutions to combine groups of building, just provide one substation, and then use much cheaper piping in between the buildings, maybe via the cellars or the garages, to connect the buildings and make it cheaper. But obviously, it's again an ownership issue. Who operates this one? And if one complains that it doesn't get warm in his house, I mean, who's responsible? It's a very tricky topic, and quite an interesting topic. Also, more I would say political or economic is as these heat transfer stations are quite expensive, and electronic metering that everybody wants for smart grids really add to the costs. We are now talking again of introducing heating flat rates. I mean, everybody tried to get away from flat rates because normally people consume much more if they just pay a fixed amount and don't get charged for their real consumption. But the argument is if you have a passive standard building, and it's even now already in our national law, which consumes so little because the building is so incredibly insulated, and then you're allowed to not to meter this building anymore. And obviously it decreases cost, and that's the main reason for this. It's not, we still don't have any regulation on the domestic hot water. This needs to be monitored, and but I think it will come. This sort of flat rates for passive standard buildings, it would make network distribution much easier. Okay, let me talk a bit about these low X concepts, basically meaning that we get away from classic district heating systems. I mean, the real classic ones have temperature levels over 100 degrees in winter. And you find them a lot in the Eastern Bloc countries. They have very high district heating rates, but very high temperature levels, very high heat losses. And sort of typical newly built networks, you find them more in the temperature range between 70 and 90 degrees. And what is here on the left side are networks which even go with lower temperature levels, maybe between 35 and 60, or even what we call now cold heating networks. It's a bit of a contradiction as such. Cold networks, which basically take the heat from the ground. It's like a geothermal heat exchanger, maybe in the range of 0 to 25 degrees C. But it's still warmer. I mean, the geothermal network is still obviously warmer than ambient air. So for heat pumps, it's an interesting option. I think, as mentioned already, underfloor heating systems are very common in Germany now. So we can heat our buildings with 35 degrees, no problem. New buildings, obviously, or very well insulated, refurbished buildings. The problem is domestic hot water. There we have a regulation for health reasons, for Legionella prevention of 60 degrees, unless the system is very small. Then you don't need to have it. But typical systems require these disinfection systems. So I'm going to talk a bit about other solutions. One solution which is now very much used in substations, in district heating substation, is to get away from these classical storage tank concepts where I think you need to heat them occasionally to 60 degrees, otherwise you have stagnant water, you have this Legionella, so there's no solution to it. But if you go to direct flow, I don't know whether that's the correct translation, to direct flow heaters, just a heat exchanger where you heat up your cold water, then you have, and the water volume in the tubes is less than 3 liters, that is our rule, then you don't need the 60 degree anymore because you have no stagnant water anymore. So, and there's now many heat transfer stations on the market which have a heat exchanger for your heating system, and then obviously you need a very high power heat exchanger for the hot water, domestic hot water. And I think that's a good solution. There are obviously, apart from these sort of thermal solutions, there are also other technologies, electrical solutions, some oxidation processes which are used in hospitals. I have no personal experience with them, but could be also interesting. I mean, it doesn't cost much energy, this sort of anodic oxidation. I can't tell you the costs, but it's maybe something to be investigated more. So that also allows you to get rid of the 60 degree requirement. But what we looked at is the right solution. You see here the heat transfer station, very compact individual apartment heat transfer stations which have all the control inside and work very well. And And this allows us to operate the network with 40 to 45 degrees. Okay, so as I said, just as in, okay, these are not spaghettis, I should make it more complex. Looking, but it looked very similar to the smart grid picture that we had before, only that now we're talking about thermal energy. And we might have some exhaust from industry, we have some solar thermal, we have some geothermal, we have some biomass, we will still have some cogeneration. And we might, as I said, we might have to think about cascading temperature levels. Maybe geothermal with temperature levels of 10 to 15 degrees C can be used in combination with decentral heat pumps. Then we might have intermediate temperature level and higher ones for industry process heat. So I think this concept of virtual plants, power plants, we should not just always talk about electricity, but also about heating. So now I'm approaching the more very concrete project. So I try to see now if we have networks and we want to integrate renewables, especially solar thermal, because as I said, biomass resources are limited. There's many different options, and I don't think there's still a clear winner. I mean, first of all, I think the big decision is it a system with seasonal storage or not? So with seasonal storage, you can go to real high solar fractions. Most systems don't have this because it's still too expensive. There are maybe, I would guess, 15 projects in Germany with all types of seasonal storage, water-based, different construction types, with gravel inside and so on. Most systems are without seasonal storage. That sort of limits the solar fraction, I would say currently maybe to 30%. In that order of magnitude, but okay, 30% is better than what we have now, which is nearly zero. And what we're discussing is now, how many pipes do you need? Do you need extra pipes for the solar system in addition to your heating supply pipes? Very often you have a large solar installation, it goes to a storage tank, and then you distribute again via the normal district heating network. That means 2 pipes extra, it's expensive. I think it will come down to 2-pipe systems because obviously 2 pipes are the cheapest. And then we're more talking where to inject best the solar thermal energy. In the return, taking the return flow, heating it up again and pushing it back into the return. This is good for heating plants, but if you have your system coupled to a cogeneration unit, it's obviously not so good because if you increase your return temperature, go back to your cogeneration unit, then your electrical efficiency drops. So that's only works in purely heating-based systems. You can do the same completely on the supply side. But this is tough for the solar thermal system because then you're talking about raising temperature levels from 70 to 80 degrees, and your solar efficiency is quite low. And I think what is still mostly done is the return to supply connection. One of the problems, technical problems, is that the pressure difference in the networks are quite high. So you need quite a lot of pumping power. You can have a few bars of pressure difference between return and supply, depending where you are in the network. The supply companies like this option because in this case, the customer or the solar thermal producer has to pay the pumping energy. In all other cases, the supply company, you see there are no pumps here involved. In the other case, the electricity company, the energy supply company needs to pay the extra pumping energy. So they like the return supply solution, and well, it costs, as I said, a bit of electricity. And then we have quite a bit of discussion of decentral heat generation in buildings because the solar systems will be on your roof, and feed in of solar heat. This is not happening now. Just now, all the solar thermal installations all the solar thermal energy gets used in the building itself. I haven't seen any project where there's a feed into a network because then you need to pay it, you need bi-directional meters, heat meters. It's all not so trivial. But I think we will have that. If we have more and more solar thermal on buildings, we need to talk about feed-in as well. So what we did now in this concrete project, the red part is an existing network in a city district which gets rehabilitated. Some new buildings are built, and this is existing. And now we're talking about a small city extension, which will be hopefully passive building standard. But at least it will be what I call this KfW 70s. Is actually it means it's a banking abbreviation. KfW is the Kreditanstalt für Wiederaufbau. It's a big bank which finances these efficiency measures. And so they even define the name of the energy standard. So this is a low energy standard, not bad, but you can go down to passive standard. So we work now a lot with urban planners, and the first concept you see on the left of the city extension, obviously for district heating it helps if your buildings are connected, if you have a common basement, and we suggested at least to have a few row houses on the right corner, so that would make it a bit cheaper and easier to integrate networks, even if it's passive building standard. And the heat density you see slightly increases. We analyze passive building standard and then the slightly higher low energy standard. And what is already in place is a heat pump. This is the main energy supply, a 200 kilowatt heat pump coupled to about 115 meter geothermal heat exchangers, a field of 50 of these heat exchangers. And in addition, there's a just conventional gas-driven CHP engine, and then for the peak loads, some gas boilers. So there's a machine house, and the geothermal field is by the side. This is already all in place. The network, the conventional network is in place. And what is very interesting, and I hope during the next years we will get the monitoring results. I mean, all substations have smart meters. I mean, so we get very detailed load profiles from every buildings on the thermal side. And what is also very interesting, there we can do some demand side management, because the supply company who runs the whole system has access to storage loading. There's domestic hot water storage tanks in every building, and they can say, well, we have energy at 2 o'clock at night, I charge now your boiler. And so they can do some load shifting from their central system. I think a topic which is also very interesting from a more academic point of view, but not just academic, we are now going very strong on three-dimensional city modeling. The whole state of Baden-Württemberg will have a 3D model of all buildings in the state. So, and we started now in this district to look very much in detail at the 3D model, and if we know by building age and standard the thermal properties, the U values, we can do very simply and very automatically a full heating energy demand calculation for the whole district, because we do the standard monthly energy balance. We have to estimate a few things like amount of window surfaces, but if you know the building age, you know more or less how much percentage windows you have, and we compared that with monitored data, and it really works well, surprisingly well. On a district scale, talking the accumulated energy calculated compared to measured is maybe 5% different. On an individual building, the error is much bigger, because then the user influence is there, but then we're talking about 20% error, but it's a very good method to see where you are, to visualize the consumption as it is, and then calculate your scenarios. What happens if you improve the U values to the overall demand of the district? So that, I think that's something to look at, very interesting development. And then we try to couple this is now a new funding project we have with network simulations, because all these network design tools are design tools. They are there to design the piping diameter when you build the system, but they're not there for annual energy simulations. But if we talk about solar thermal, we need to know every hour what is happening, who's injecting what. Is there a demand at the same hour? It's not enough to do just energy balances. So we have now a project to develop a dynamic heating network model, which has to be a bit simplified, more simplified than the design tools, but that we can really see what is the difference if all our consumers are located as they are? Or is it not better to bring them closer, the main consumers, closer to the power plants? Then you have less heat losses. So we can study very much in detail what happens to the heat losses, to the electrical pumping energy, just depending on how your distribution of consumers in a district is. I think it's very important to do that, and then calculate solar thermal injection. So I have to go a bit faster, I think. Okay, so now I show you some results of these different network analyses we did for this very specific district. Obviously, the connected power depends on whether you choose a low energy standard or passive building. I mentioned this, but I want to show you now the options that we analyzed for the network extension in this district, which will be a low energy anyway, maybe passive standard. And so the classical option would be just to continue with the high temperature network, which means high temperature, 70-degree supply temperature, 40-degree return, some decentral domestic hot water tanks in every building, and that's it. That would be the standard solution that the supply company wanted to do. Then, as it is a research project, so they should do something a bit more innovative. We try to convince them to at least go to a medium temperature network, which means a supply temperature of only 40 degree, return 20, to better use the network mass flow. You might need a bit of extra electricity for the hot water, because 40 is already the lower limit of temperature. So there might be a bit of flow through electrical energy requirement, or even go to a very low temperature network with 25 degree, but then you need a heat pump at least for your domestic hot water, and probably also for the heating system. So that means more investment. So these are the options, and this low temperature network basically means you take the return temperature of the main network and use it for the city extension. It's not for free. You need an extra pumping station. So all in all, it will cost maybe 35,000 euro. It's still a reasonable cost. And the big advantage I see is if we have such a low temperature network, then it's very nice for solar thermal energy integration. Because if you talk about 40 degree supply temperatures, you can really run a flat plate collector with good efficiency. And I think that's the main argument, because you'd see the CO2 emissions. I was surprised about the results. So obviously we had to do the cost calculation. So the total cost per kilowatt hour in the existing district was about 8 cents per kilowatt hour. Full costs these are, and you see the city extension will increase the price, the overall price, because the heat demand is so low, and you still have the same investment cost. But you see all these, whether you go for high temperature, medium temperature, low temperature networks, more or less the costs are the same. I would say it doesn't really make much difference. Only the heat pump option is much more expensive, because it's not just the investment of the heat pumps. Here we sort of distinguish between capital costs and operating fuel and other costs. And you see the investment costs of the heat pumps are not that much higher, but now you need to heat up basically all the water from 25 to your heating temperature, and you need much more fuel. You have much higher electricity costs. So, and all the others, as I said, are very, very comparable in terms of economics. And then obviously what we expected, if you start reducing the temperature level of your network, the heat losses go down. It's fairly obvious. I mean, you see again the two building standards. If the district is a passive building standard district, and you build a conventional 70-40 degree network, you have 30% heat losses. It's not marginal. It's really significant, and that's why these medium temperature solutions are interesting, because then you bring down your heat losses to, even on a passive standard district, to 18%. Obviously, if you go further down, the losses are even smaller. So that's good news. So I would definitely recommend the medium temperature system. And then I saw the results of the overall CO2 emissions for these different network solutions, and I couldn't understand it. I thought the researcher had made a mistake, because if you looked at the conventional solution, the total CO2 emissions with the standard network extension, with high heat losses, 30% in the passive standard, were lower than all the medium or low temperature systems. So that was bad news. Although we have much higher heat losses, we still didn't reduce emissions. And well, then we looked very much in detail in the results, and the explanation is the electric flow heaters, direct flow heaters, which are needed then, or depends a bit on the assumptions you make. Maybe it's not all, we could save there a bit, but you need just more electricity for your domestic hot water if you bring temperature levels down. That was the main argument. So basically the message then was the costs are more or less the same, you have lower heat losses, but you don't necessarily reduce emissions because you will have to look at your domestic hot water. But then solar thermal could come in. And so now we're trying to convince the energy supply company to invest in solar thermal. They don't really like it because they say, well, we have a gas cogenerator, we have so much heat in summer, we don't get, it sort of decreases the economics of our cogeneration unit. And I think they will only do it if we can make sure that their cogenerator is used elsewhere. So we're talking now about an extension of the network into a neighboring old city quarter, and they could dump all the heat in summer. But it's an issue, so it's not easy to bring in solar thermal if you have cogeneration engines around. Here we talked about this sort of heating flat rate also, which would be nice for the supply company because they could cut their costs. The substation investment would really go down depending on what type of network you have with the flat rate, especially for the medium temperature networks. You could really go for cheap substations, but they are not sure that they want to do it because it's also a customer relationship issue, whether you really trust your customers then not to open all the windows all winter and heat a lot, and they find it risky, so we'll see. Okay, to conclude, I think this concept of smart grids or virtual power plants is very important also for the heating sector, because if we have networks, then we can much easier integrate renewables, all forms of renewable heat sources, solar thermal, and so on, and we can make use of demand-side management much better than individual buildings. Well, I think solar is obviously much easier to integrate if you have low temperature networks, and we need some more work to be done for distributed generation on the thermal side, new heat meters, new control strategies, and yeah, I think the last one, what did I want to say? Yeah, the first topic I talked about, if you have reduced demand, then we need to adapt our distribution and supply structure to make it efficient enough to justify the extra costs for network solutions. Okay, thank you very much.